Well, hello everyone. Welcome to another adventure of understanding schematics. I'm your host. No, I'm kidding. So let's talk about meters, okay? I currently have three different meters. Actually, I've got five if you want to count it truthfully. Okay, I have a meter that I can check pressures with for gas pressures. That's a meter. I have a multimeter that I carry around with me. I have a amp probe. Um, they all check a various different things. This is actually the meter that I carry with me, um, and it was very cheap. Um, I'm world's worst. I'll be honest with you. I do one of two things. I either lose it, break it, or can't find it. So I keep a meter, and I've got an expensive meter, but I don't normally carry it with me in my truck. The problem is again the heat. I actually did buy a new meter that I just got that I'm going to start carrying it around with me. This one actually, uh, let's see, there it is. This one actually, it has a download so that I don't have to have batteries for it. That's one of the things that really goes bad with a meter is you don't have batteries. My batteries, I have to keep spare batteries in my truck, but this way I can my voltages are I can get everything that I need from from one meter. So that the meter, both of the meters that I just showed you, will actually check oven temperatures. That's one of the prerequisites that I have to have if I need something that I can check oven temperatures with. The other meter that I carry, two meters with me in my truck. One is an amp probe, like I said. It'll actually check the the heat. So I've got that, and I also have the one that has the thermometer, the thermostat in it, so I can check that. So I always keep a meter with me. Like I said, I've got some very very cheap ones. Harbor Freight. Whenever I got one that I have that I leave out in the garage, if I need something to do a quick voltage check or quick resistance check, I've got that cheap meter right there, and then I don't have to. I'm not depending on it with my life. Um, so meter basics. Basically, a meter is designed to measure three properties found in a working circuit. Okay, where it's designed to check resistance, check voltage, and check current flow. Okay. This is why a meter may be called a multimeter. Okay. Like I just showed you, the one that I had, that's my multimeter that I keep with me. Um, I've always got it with me in my truck. Now, like I said, you got to keep a spare set of batteries, both the little AAA's and the 9 volt. I don't want to. I want a meter that I can check anything with. So that does it with that. My current flow. I've got it all set right there with that cheap meter. But even my cheap, you know, 495 meter from Harbor Freight, it'll do basic stuff. I mean, I like I said, I'm not going to use this meter to bank on that. It's all going to be 100% correct. Um, but those are all examples of multimeters. Okay, they perform multiple functions. They measure different kinds of voltage and current. Okay, this even this cheap meter right here, the 495 one from Harbor Freight, it checks DC voltage, it checks AC voltage, it checks resistance. Like I said, it may not be the greatest meter in the world, but if I just need a quick look, this is it. It actually has one of the functions down here on the very bottom. It's got the buzzer on it, so if I'm checking resistance, I can set it for the buzzer, and if the circuit's good, it'll buzz. None of the meters that I have just kind of go beep beep. They don't do that. Mine buzzes, and then whenever I take it off, it stops buzzing. Okay, so let's talk about resistance. Resistance is the opposition to current flow as a component. It is measured in units called ohms. Okay, and all electrical components or devices have a resistance value. The symbol for ohms is the omega symbol. Okay. Examples is an inductor, a circuit board, a power supply, a resistor, a diode. Now, most circuit boards and power supplies have resistors, diodes in them. So if you're looking at a power supply board, it's all going to be there. And a circuit board they're going to be there. So we're going to go next to voltages. Okay. The electrical component and potential differences between 2 points is measured and it's called volts. Okay. The symbol for volts is V. Okay. This potential can be either DC, which is direct current, or alternating current, AC. Okay. The symbol for DC current is DC, of course. And if it's AC, that's alternating current. Okay. So here's examples down here. DC voltage would be a car battery. There's a lot of DC voltage in today's refrigerators. There are DC voltage on just about everything anymore. Even your washers, your dryers, your refrigerators, your freezers, all of those have a component that has a DC power source. Okay. Usually it has a separate board. The main board has an AC board, and then there's a breakdown and it goes to a DC board. Okay. So my AC voltage is an example of that is line voltage that powers all of your home circuits. Okay. So if you have any questions, let me know. Okay. Current is the flow of electrons through a conductor wire at a certain rate based on voltage source provided in a resistance of the flow of the current circuit. Okay. In the United States, we operate on a 60 and in the UK and almost everybody else operates on a 50 hertz instead of 60 hertz. Okay, so just like voltage, current can be either AC or DC based on the voltage source of the current. Okay, an example would be the light bulb of your home. When you turn the light switch on, you complete the circuit path and from the source, which is the $120 volt fuse box, through the switch into the light bulb and then back to the fuse box, which is the ground. Okay, this circuit uses AC current. You're talking about light switches. That's usually where it's cut. You actually break the neutral and not the hot leg. That causes the switch to last much longer. My house in that I have in Daytona Beach is it's 1972 is when it was built, and they broke the hot wire. Okay, so circuit values. These properties found in every circuit can be different values. Okay, very large, very small. For examples, a component's resistance value can be millions of ohms of resistance. A unit of 1 millionth of an ohm is called a mega ohm. If you have a different value of current and the resistance is opposing current, is the circuit is very large, many times the current is in the circuit can be very small, units and millionths of an amp. Okay, this amount of current flow is called a microamp, and it's simple. And the symbol is, you see the little symbol there. Okay, where do you see that symbol a lot? If I go and I pull a capacitor, it's measured in the micro ohms. Okay, the microamp, that's what it's measured in. So in your microwave oven, that's where you're going to find that capacitor. And then if you happen to work on outside um, air conditioning, you're going to find that's what you need to know is how many microamps do I have. So it gives me that gives me that information. Okay, so if you have something that has a capital T, okay, that's a teraamp. So I'm going to multiply that by how many, by what? That's a trillion. Okay, a gigaamp. I'm sorry, that's a that's a whole lot of zeros. Okay, a gigaamp, you measure that by millions. Nope, one, two. Let's see. Nope, that would be trillions. Okay, mega amps are measured by a whole lot of zeros again. Okay, the kiloamp is measured by 1,000. Okay, if the mega amp is a million, by the way. Okay, the millimeter, the million, the little small m is a millimeter or a milli. That is divided by 1,000. Okay, the microamp is the SI, which is you see the symbol there. I'm going to divide that by a million. Okay, so the kiloamp is basically is whatever the amperage. If it's a kiloamp, you're going to multiply that times 10 to the third power. Okay, if I'm going to multiply a mega amp, I'm going to get that voltage that times 10 to the sixth power. Okay, if the gigaamp is 10 to the ninth power. Okay, the teraamp is 10 to the 12th power. Okay, so these are the values that we have for circuit values. Okay, so if the prefix used is a capital letter, that typically represents a unit of measure greater than 1,000. Okay, could be it's greater than 1,000. Okay, if the prefix is a small case letter, that typically represents the unit with a measure of less than 1. So it's a fractional unit. Okay. Okay. If the prefix used is kept, oh, that represents a larger. So this is the same thing. Somehow it got mixed in together. Okay. So the table of circuit values. Here it is again. So that's in billionths. The mega is in millionths. Kilo is in thousandths. Okay. The fraction, the mill is thousandths. That's 10 to the minus 3. The micro is millionths, and that's 10 to the minus 6. The nano is billions, and that's 10 to the minus ninth. The pico is 10 to the minus 12th, which is trillions. Okay. Like I said, the pico is if you look at the micro, that's where our thing is. Okay. So this table provides definition of each unit of measure mathematically. This is the mathematical equation that it is. Okay. So if you have any questions, once again, let me know. Okay. These are voltages. Okay. If anybody has any questions, go ahead and put it in the comments section, and I will get to it whenever I see them. Okay. So we're on the examples of circuit values for voltage. So a gigavolt is 1 GV, okay, which is 1 to the 10th, which is 1 times 10 to the ninth power voltage. Okay. A megavolt is 1 to the I'm sorry is 1 to the is 10 to the minus 6 10 to the plus 6 power. Sorry about that. Okay. If I have 1,000 volts, that's 10 to the third power. Okay. That's a kilovolt. If I have just a regular volt, that's 1 times 10 to the 0 power. Okay. Or that's just a volt. Okay. If I have a point 1 volt, that's 10 to the minus 1 power. If I have the millionth volt, which is the 0.001 volts, okay, that would be 10 to the minus third power. Once again, we're talking about voltages now. Okay. If I've got a microvolt, that's 10 to the minus 6 power. You can see right there how many zeros are behind the are in front of the 0. So if I have a nanovolt, I have one which is 1 times 10 to the minus ninth power. And if I have a picavolt, that is 10 to the minus 12th power. Okay. So here's our examples of circuits right here. So here's our gigaamp, and these are just the different ways that I have laid them out. Okay, these will be readily available to you whenever you go back and want to review the class. Okay, so here's the resistance. Okay. Right here, if you notice, that's 1 times 10 to the ninth ohm. That's a giga ohm. If I have 1 times 10 to the sixth ohm, the sixth power ohm, that's a mega ohm. If I've got 1 times 10 to the third power, that's just a regular kilo ohm. If I have 1 to the 0 power, that's just 1 ohm. If I have 0.1, that is 1 times 10 to the minus 1th power, and that's just a regular 0.1. That's a regular 0.1 ohm. Okay, so we've kind of gone through, and I thought that I had gotten rid of all these questions. So right here is an old. I've got one of these somewhere in the barn. And it's a little bit, it's just one of the old needle meter. Like I said, I have one of these down in the barn somewhere, gathering dust. These were really, whenever I first bought one, it was about this big, and it had a spot for my leads, and it had my meter on the right side. Okay. If an analog or needle meter has only one range of measurements on its face, it would be very hard to get an accurate reading. In order to make it easier to get a very accurate reader, meters use ranges of measurement. Some of the meters have to be switched from a range manually. When this is when the user rotates a dial to select the proper multimeter range so that the meter can display the value, okay, and so that it's read properly. In this example, okay, the DC voltage meter ranges are from 0 to 0.1 DC volts, or I've got a 0 to 0.5 minus 0.5 DC volts, and I have 0 to minus 2.5. And if you look on the right side, the left side of the meter, it shows you exactly where each one of those each one of those were. I had it circled and I didn't like the way that it did. But if you look on the left side of the meter, that shows you your DC voltage range. Okay. This one came out a little bit better. It's kind of like this one right here. This is the cheap meter. Okay, but you get the exact same thing. This meter right here doesn't have the needle. It's a little bit harder. It's a little bit easier to read than this old meter, because this meter right here, if you had bad eyesight, you had to really get down and look at it. Okay, and then if you look at the different levels, you had to measure that. Okay, so you had to know where you were at and what you were actually trying to check. Okay, this meter made it a little bit better. That's what this meter is right here. Like I said, this is a Harbor Freight, basically $5 meter. So the meter's rule is to accurately measure the units. Okay, if a digital or numeric meter had only one range of measurement on its face, it would be very hard to get an accurate reading. In order to make it easier, you select the range that you want. This is DC voltage range right here, this example. And if you look at it, it tells you 0 to minus 0.2 DC volts, and then 0 to 2.0 volts. And then I've got 0 to 20 volts DCV. Then I've got 0 to 200 DCV volts. And then I've got the last one is 0 to 1000 DC volts. Okay. Today's meters make it a little bit easier. Here's circuit values. Okay. Once again, it's I'm going to use the numeric range, but this meter right here will actually tell me. If you look at it, it's only got, you got to know what you're looking for. Looking for kilo ohms or mega ohms or ohms or DC volts or AC volts. I have to select that on the meter itself. Okay. To make it easier to measure, today's multimeter meters have an auto range. Okay, this is configuration of the meter senses. The values of the property being measured will set itself to the proper range to provide an accurate reading. Okay, like I said, they've got simpler and simpler and simpler. The meter to the right is an example of an auto ranging meter. You can see why the meter only allows the user to select the property they want to measure, but there is no ranges that they have to select. Okay, so if you look at this meter and you compare it to this meter, you can see the difference. Okay, now one of the meters that I have currently also, I can actually just have it will actually, if I'm looking for AC volts, I can actually just touch it to the power supply, and it will actually read the AC side of the voltage. Okay, so this is our meter's role. Okay, is to the operating power source from the unit being diagnosed. The most common method is to unplug the unit from the wall outlet, turning it off. The appliance's power to the circuit at the breaker box. So I'm going to disconnect the power if I'm going to measure something in resistance. If I try to do it without disconnecting it, the other thing is if I have a capacitor that is in the circuit, I have to release the capacitor voltage, because the capacitor holds voltage. You can actually blow a meter up if I'm just checking it, and I don't have it shut. I don't have it if I don't have if I don't have the power shut off, and if I haven't discharged the capacitor, I can blow this meter up. Okay, so this is our resistance. Once the power is removed, you can use the meter's ohms function and the meter's internal battery to check a value of the component's resistivity value. Okay. If you notice right here, This one is set to ohms, and I've got 1 ohm is what I'm measuring. Okay. So if I'm talking about, let's talk about resistance. Okay. This is a fuse, as everybody knows. Okay. If I have a good fuse, I have an open circuit. Okay. So that would tell me that I have less than 1 ohm. Okay. So that would tell me that my fuse is good. If I have a bad fuse, I would have 1.0 ohms, or it may just be a 1 ohm. That would tell me that my fuse is not good. Okay. The component that can have its resistance function for functionality would be a fuse. A good fuse would show a minimal, less than 1 ohm value of resistance. A bad fuse would show an infinite or open reading. Okay. Same thing if I'm checking a compressor. Okay. That's how I know if it's good. I can actually check a compressor with a continuity function. Okay. Another feature on most multimeters can be used to check for low resistance is the continuity function. By the use of the beeper function, the technician can check low resistance components like fuses or coils to ensure functionality without seeing the meter's display. If the component is good, low resistance, then the meter will beep or tone. Okay. If the component has failed or the component's resistance is no longer low, the meter will not beep or tone. Okay, this will indicate a failure. Like I said, I can check a compressor by going from the common to the open, common to the start winding, and the common to the run winding. Okay, so all I'm doing is completing the circuit. That's all that I'm trying to do. That's what the continuity function does. The continuity function, the nice thing about the continuity function is I don't have to actually be looking at the meter. The meter will actually tell me, hey, it's good by giving me the tone. Or if I don't get a tone, I know that it's bad. Okay. The first thing that I always do, though, is I always take my meter leads before I get ready to check anything. I just go ahead and touch my 2 meter leads together. And if it beeps, then I know that my meter is reading properly. Okay. Okay. So checking a magnetron on a microwave using the continuity check, this will actually tell you if the magnetron is good. I will caution you, um, in my endeavors, I have actually misdiagnosed because I got a beep and the magnetron was actually bad. You have to always go back and check, but this tells you exactly if this meter, if the you can't. It's not an exact thing with a magnetron. Okay, I've gone through and checked everything, and nothing checked failure. As soon as I replaced the magnetron, the microwave started working. So just be cautious whenever you're checking a magnetron, to tell you that if you get the beep, you still may have a bad magnetron. Okay, so checking a temperature sensor. Another component that can be used for its functional state is a temperature sensor. Okay, an example, they all use them today. This whenever I put this program together, I was doing a Samsung class, so I added this slide into this one because it's very important. But Samsung uses in their refrigerators. Almost every manufacturer today uses a temperature sensor. Okay, um, there's sensors. There's a high limit sensor that you have in an oven. You have high limit sensors in a microwave. Almost everything has sensors that are in it today. So you need to know how to check a sensor. Here's the interesting thing about excuse me, about the temperature sensor in a refrigerator, okay? As the temperature that surrounds the sensor goes down, the resistance value of the sensor goes up. That's something that you need to remember, okay? Below is an example of the checking the sensor from the main board as a component out of the unit, okay? So what I'm going to do is I'm going to check it. I'm going to see that whenever I go in, and the first thing that I check is at room temperature, which is about 77 degrees, I would get about 5.0 ohms, okay, of resistance. Okay, that's at about 77 degrees in a home. Okay, if as that sensor cools down, okay, you can see that at 35.6 degrees, I now have a resistance of 12.2. Okay. I'm getting about 2.75 volts. Okay. As it continues to cool down in the freezer section, and I get down to about a 2.2 um, uh, temperature, I'm going to have 30.9. Okay. Or I'm going to read about 3.78 volts. Okay. As it goes down, most people's refrigerator usually is set somewhere around 0 to -4. Okay. So if you look at -4, I now have 32.4, okay, ohms, or I'm going to have about 3.82 volts. Okay. So you need to remember this as you're going through. Okay. The sensor tells you right there, as the temperature decreases, my resistance goes up. It's not the opposite. So some resistors, you have to know which ones are which, because some of them do actually, as the resistance, okay, as the temperature goes down, the resistance goes down. So you have to be sure that you consult your manual so that you can tell that I'm got the right information. You never want to just think that you've got it right. That's the way you make mistakes. Okay. AC voltage, measure the voltage of the circuit. As you see right here, as this one was measured, this one is reading 120.7 volts. Okay. So, like resistance, voltage measurements are taken across the component or between two measurement points. Okay. The circuit is the circuit's functionality. Okay. When measuring voltages, the power for the circuit is an external source, like 120 volts line voltage from a sink outlet, not from the meter. Okay. So what I'm trying to convey to you there is, okay, I've got a positive and a negative. Okay. That's the way that I'm completing this circuit. My positive is one of the wires. My negative is one of the others. So on this circuit, if you're looking at it, the neutral is the black one. Okay. In the example, the technician is in this one right here. The technician is checking 13 volts DC. Okay. This is out of the power supply. Okay. This is showing 12.71 voltage DC. Okay. So you need to make sure that you have it set to the ohm scale. Like I said, this will actually blow your meter up if you mess it up. Okay. Or you'll get a funky reading and it won't work. Okay. In this example, so we're showing right here that I've got 12.71 ohms, and it's whenever this unit is powered on, that's what I have. Now, what I can tell you is I can tell that this is DC power supply because the wires are very small compared to an AC power supply. If I was looking at the AC power supply, the wires would be larger. Okay. So measuring the current, okay, using a clamp on meter. So if I'm going to measure current draw on a dryer circuit, an example would be, use I would grab my clamp on meter, which is what I use it for. Okay. If I'm going to do this, it'll tell me how many amps I'm pulling. A dryer normally requires, if I have a gas dryer, it takes 3 amps for that 3.5 amps for that circuit to close. You may end up having only 2.7 amps, and the gas valve will never fire. It looks like it looks like the dryer should be firing. So don't just take advantage and say, hey, well, I've got my glow plug, or my igniter is heating up, so it's good. Don't take that for granted. You have to go in and check it using your amp probe. Okay. So what I would do, I don't surround both of the wires. I only take one of the wires and clamp onto that. Okay. The clamp uses inductive sampling and will turn on, converted to the corresponding current draw. That would create the inductive sampling. Okay. I took the other one out so that we could have this presentation, because the presentation that I had was for a whole lot of like a in-person training, and this one has limited me to about five MBs, because I can't. It won't download any more than that. So I removed that dryer, um, the example. So let's talk about Ohm's law. Okay. Ohm's law states the relationship between electrical current and potential differences. The current that flows through most conductors are directly proportional to the voltage supplied to it. Okay. Who discovered this? George Simon Ohm, a German physicist that was the first to verify the law experimentally. Okay. Ohm's law states that the voltage across a conductor is directly proportional to its current flowing through it, provided all physical conditions and the temperatures remain constant. Okay. So let's talk about Ohm's law. This is the Ohm's law triangle. Okay. So if I'm trying to, I didn't get, this is the wrong one. Okay. This is whenever I put it, I messed it up. Okay. So Ohm's law is V equals IR. Okay. Where V is voltage across the conductor, I is the current flow through the conductor, and R is the resistance provided by the conductor to the flow of the current. Okay. So if I'm going to do this, V equals I times R. So V equals I times R is right here at the very top. So this is what I will find. Okay. So if I'm gonna invertly look, oops, I went the wrong way. Sorry. So if I'm gonna chart right here, okay, if I'm looking for I, okay, if I'm looking for I, which is right here, that is going to be V over R. So that's telling me that if I'm looking for I, I'm going to find the voltage over the resistance. Okay. If I'm looking for resistance, I'm going to is V over resistance equals V over I. So this way, if I have two of the equations, I can actually be able to find out what it should be. This is good, so that let's say that I'm checking for the voltage, okay? Because that's the easiest thing. So if I have the I, Okay, once again, if I have the I, what was the I? Oops. Okay, that's the current flowing through the conductor. R is the resistance. Okay, the voltage is the I. Okay, so if I'm looking for V, I get I times R. Okay, so Ohm's law states that the voltage across the conductor is directly proportional to the current flowing through it, provided that all physical conditions and temperatures remain constant. It is certain components increasing the temperature, okay? I'm sorry, it increases if I have the current and it raises, um, increasing the temperature, increasing the current raises the temperature. Okay, so if I increase the current, I'm raising the temperature. Okay, which is exactly what we saw with the resistor that we showed. Okay, an example of the filament of a light bulb when the temperature raises as the current increases. Okay, so as you turn the light bulb on, you know that it doesn't go automatically all the way. You get a little, it gets a little. It starts, and then you can see that it get full power. Okay, so once again, here's Ohm's law. Okay, you can do it one of two ways. There's the voltage, which is I times R. If I'm looking for I, I'm going to get V over I, V divided by R. If I'm looking for resistance, I'm going to get V divided by I. So it's all right here. You'll have this if you need it later on. Okay. So let's talk about power sources. Okay. Like I said, we've got both AC and DC power sources. Okay. AC power sources is the alternating current power flows in two directions and is noted in the symbol below. Okay. Here's your typical 110 power cord that we see. I have the neutral. Okay, and then I've got the line voltage, and then currently today we have a ground. The house that I have in Daytona doesn't have a ground. Excuse me. So if you look right here, here's line voltage. The one on the right is 240 volts. So I have an L1. I have a neutral. The ground runs off the neutral. Usually, like on a dryer, you disconnect the neutral and you have a ground wire and a neutral wire that you have to hook properly correctly. Okay. Then I've got the L2, which is I have two hot legs and one neutral and one ground on today's. Okay. On a DC power source, it only flows in one direction. Okay. The symbol for your DC power source is right there and it shows you plus and minus. If you look there, it says the symbol for ground is right there in the circuit. If you look at the AC power source for the 240 volts, you'll see that there is the US. It says US under it, right next to it, and that's the ground. Okay, so let's talk about batteries. Okay, a battery is a common type of DC power. Okay, it's made up of parallel short lines and long lines. The long lines are the positive side of the battery, while the shorter are and the negative side are shorter. Okay, they may have the positive symbol to help identify the power source. Okay, so you see the power in the example to the right. Okay, this is a battery. Okay, longer lines are the one on the top, and it's got a little plus symbol, and then you notice that the shorter lines are are the negative. Okay, so sorry about that. My battery fell. So if you look on your batteries, okay, you got a positive that it shows you the positive right here. Okay, which that would be the longer lines. Okay, and then I don't have anything on the negative. On the negative side, I don't have anything down here. It just shows me the one way. This is like I said, this is a battery. Okay. Now they are in a circuit, so you need to look at your circuit and you need to know that this is a battery. It will show you. Okay. So here's a terminal. Okay. Terminals are a connection point to an exterior circuit and are noted by the following matter with an empty circle. See how the circle is only on one side. Okay. Then the terminal connections are different and they are noted with solid circles. Okay. We're going to get through these. And as we go through right here, here's your terminal connection. Okay. It's right there at the very top. And then your terminal is right here next to the diode. So you've got your terminal connection and your terminal. Okay. So let's talk about switches. There are two types of switches. One is a single pole, single throw switch. I'm sorry, I misspelled that. Okay, this is the on-off switch on a wiring schematic. This is what you see. So a perfect example of this would be whenever I hit the start button on my dryer. It's a momentary switch that pulls and closes the circuit, and whenever the dryer completes its cycle, it releases and it no longer is now working. Okay. So the top switch shows the current in the open position, and the bottom shows that the current in the closed position. Okay, that is a single pole, single throw switch. If we have one, we have a single pole, double throw switch. Okay, this directs current to different parts of the circuit. The route of the power is determined by the position of the switch. So in this following switch, I have power to the top leg of the switch. I have no power to the bottom leg. Okay. Whenever I get power to the bottom leg, that switch will swap and it's on the bottom. Okay. A momentary switch. Okay. That's what I'm talking about whenever I say your start switch in your dryer. The momentary switch remain open or closed while the switch is being pressed. The common type of switches that use push button style, the top diagram shows the switch to be normally open. The bottom diagram shows that it's normally closed. Okay, these switches have two inputs, and these two switches have two inputs and two outputs. Since these are single throw, this allows the switch to control the power to two outputs, okay, simultaneously. The symbol for this type of switch is below. You'll find these in your microwaves, okay, for your door switches. Okay, double pole, double throw. Okay, these switches have two terminals, the current, and four terminals for the output. This allows you to switch the path of the two input currents to the four separate output current paths. So here's a schematic symbol for a double pole, double throw switch. Okay. So here it is in a circuit. If you look at the one on the top left, that would be your single pole, single throw switch. Okay. If you look on the bottom, there's your start diagram. On the very center of it, it says start. That's your start button. That would go ahead and that would be depressed, and that would mean it would start the motor as it completes all the circuits. Okay, let's talk about resistors. A resistor provides a restriction of power to a circuit. For example, the US resistor is on the left. Okay, the one on the right is for the international symbol. Okay, you may see the right example more due to more of the inputs that we have. A good example of that is like Samsung. Okay, you're going to see those more in the Samsung circuits. The technical writing department at Samsung does the best job that they can, but you will sometimes find that resistor is shown as the one on the right. Okay. Another thing is a variable resistor that can increase or decrease the power depending on external input. Okay, a thermistor and photosensors are examples of a variable resistor depending on temperature or light. See the examples below. Left is the US, international is on the right. Okay. So I'm going to pause just there for a second. Does anybody have any questions? I'll take just a minute here. Okay. If you have a question, put it, like I said, put it in the comments section, and I will get to them as we go through. Okay. Potentiometer. Oh, if I could only say that word, potentiometer. Okay, is a three-terminal variable resistor that is used to adjust voltage and current to the circuit. Okay. The arrow represents the output voltage is taken from. The two terminals are V plus and ground. You see the symbols right here. So what's an example of a potentiometer? Okay. I don't have any in my house, but one of the things that a potentiometer you can do is a switch on the wall, and you actually turn the switch and it adjusts like fan speed. Okay. So, photoresistors is a light independent resistor. It's light sensitive resistor that changes resistance, that changes with a variable amount of light. It shows you right here that this is the example of a photoresistor. As you're going through, you're going to need to know that in these examples. Okay. So here's one of the things that you're going to see a whole lot of, okay, is a capacitor. Okay. What does a capacitor do? It stores an electrical charge. If it is not polarized, okay, that's a non-polarized capacitor. I have no polarity, so it doesn't matter whether you place the hot side on the negative or the positive side. They usually have a smaller value. Okay, that's your example right there. Okay, if I have a polarized, okay, that does matter which leg of the circuit they are connected to. Okay, they show a higher capacitance than a non-polarized counterpart. And so the symbol right here, it shows you there's the positive and the negative. So example would be your battery. Okay. Here's a diode. You're going to have to pardon me. I have something in my throat. I have a tickle and I can't get rid of it. Okay, a polarized device allows current to flow in only one direction. Okay, we have an anode and a cathode. Okay, the positive anode and the negative cathode side, the flat edge of the triangle is the anode side. Okay, the line is the cathode side. So whenever you have a diode, you're going to see this symbol. Okay. So if we go back to that example that we had, this one right here. Okay. Oh, I'm sorry. I thought that I had put a diode in that, but I didn't. Huh. Sorry about that. That's my bad. Okay. Inductors are passive components that create a magnetic field when current flows through them. Okay. This is a symbol for an inductor. Okay. Okay. Here's a transformer. You're going to find these in microwaves. Okay. You're also going to find them in a lot of the dryers, washers. Almost everything has a little transformer in it nowadays. Okay. But the transformer voltage, what happens to it? Um, we step it up the voltage. Okay. Either side, they are made of two coil wires wrapped around an iron core. The symbol reflects that these two coils on each side are the iron core in the center. So if you look at the one on the left side, okay, if we go back to this last one, this inductor, see this one. Now, if you look right here you can see this inductor right here on the left and the inductor on the right. And then, like I said, these are examples of a transformer, and there's transformers and everything. Usually there's a high voltage and a low voltage side of the transformer. Okay. Then I have a relay. Okay. Relays are electrically operated switches that are basic electromagnetics. And they are open and or closed when the current is applied to the coil. Okay. Can you identify these parts? Okay. I got to it. It was just very much later. So if you look right here, there's no line, but there you can see the triangle. Okay. So we have to remember what everything is. Okay. So your diode here. Okay. What's a wiring diagram? A wiring diagram is a visual representation of a physical connections and a physical layout of an electronic circuit. It shows how the electrical wires and components are interconnected and can also show where the components are in the system. Okay. So here's an example. This is a touchpad. So this is a microwave touchpad. Okay. If you see right here, here's our the transformer right there at the top. Okay. So these are all of our touchpads information. Okay. Does anybody have any questions? We have come to the end of our presentation. Does anybody have any questions? Okay. Thank you for all of your attention.